Excellent. Okay, so let's start with just a little bit of review. What is this called?
Truth table.
A truth table. What is this a truth table of? And. This is A and B. What does this symbol mean?
Or
XOR. Exclusive OR. What's the truth table? Where do you start? What's the zeros? 0. It is not OR. Is this?
1.
Yes. This. This. Not true. Absolutely. Okay, now we're going to get a bigger truth table going on here. Some terminology. This is your least significant bit, your LSB. This is your most significant bit, meaning they're the biggest number. If that changes, it changes the most you can change that number, right? When drawing out these truth tables, they're pretty big. There's an easy way to do it. You start out with the least significant bit and just go 0, 1, 0, 1, 0, 1, 0, 1. The next one you go 0, 0, 1, 1, 0, 0, 1, 1. Next one 0, 0, 0, 1, 1, 1, 1. Right? You can draw them by columns because there's definitive patterns that happen throughout. You just get more and more sequences of them. So let's create a truth table here. Just take a moment to do it yourself. I want you to write the truth table of this where true is a prime number. Remembering that 1 is not prime. Okay, 0 prime. What goes here? 1, because 2 is prime. 1. 1. Excellent. Let's double check that. 0, 0, 1, 1, 0, 1, 0, 1. Yep. Cool. So this is the truth table for a prime number, 0 to 7. What we then can do is we can write an equation that represents this truth table. We do that by finding these, which we call minterms. And what we say is for each minterm, we're going to have a sum of products. What that means is we're going to build up from products. So the products are, if we look here, not B2, B1, not B0. So every single one of these, and you can write it either direction, B2, B1, B0. Now the thing is, I know that there's 1, 2, 3, 4 minterms. For minterms, each of them have the same bits in them. So the first midterm, as I said, is not B2, is B1, not B0. So if that is true, F is 1. And all of those others are false. Which once we finish writing it, right? So the next midterm, is not B2, but is B1 and B0. The next one, the only one is not is that one, and the last one, they're all true, right? So each of these is a minterm expression. And for each one of these, only one of these can ever be true at a time, right? So this is true, or this is true, or this is true, or this is true. You will have, I believe in your homework, a product of sums, which is where you do the same thing, but instead it's built out of and so on. The sum of products, the product of sums. This you use zeros for. They end up being functionally equivalent. Another way to write this is, you'll see this notation. So this is saying it's a sum of minterm 2, 3, 5, and 7. So it's 0, 1, 2, 3, 5, 7, right? You can also write that as the sum of minterms 2, 3, 5, 7. These are all valid notations. Similarly, max terms is what we call those zeros, where you would have F is equal to the max, capital M, of the same type of thing, except for inverted, where you're having 0, 1, 4, and 6. That is also true. The symbol that they like to use when they do the sum is not always this big M. Sometimes you'll also see the Greek letter, I forget. It's not really pi, it's like, I don't remember the name for that one, but max terms are rarely used in textbooks. For whatever reason, almost all examples use min terms, but you need to be aware that max terms exist. Now, I'll just give you a second. I gotta erase this.
So, like, min terms are the ones with like the 1, 1, 1, like in the
Yes.
2, 3, 5, and 7 spot.
Yeah. So min terms are any time you have a 1 for a given row of a truth table.
And then max is the opposite.
Exactly. Yes.
And you were saying that in the textbook they mostly use min terms.
Mostly use min terms. And that comes out of something that we'll learn later, which is called K-maps. In fact, we might get that today. That'd be really fun. Okay, so there's a bit of a problem with this in that it's huge, right? And we can and will learn to turn this into digital logic. In fact, turning this into digital logic is really easy because we know that these are all ORs, right? So let's write a big OR gate. We remember these, right? And it has 1, 2, 3, 4 terms. Big OR gate. And each of those ORs is attached to an AND gate. Like so. That's this term. Right? So now I have the OR of all of those ANDs.
So you can have an OR gate with 4 inputs?
Or 8 or 20.
Oh, you can? They have
Yeah.
chips that come like that?
Well, if you think about an OR gate, what is the difference between those two?
Oh, so you can make a 4 input OR gate with other...
With 2 input OR gates.
Oh, okay.
Yeah. Right, because as long as any one of those is 1, that becomes true, that becomes true, right? But we don't like big circuits, partially because when you sit down on the bench to design them, they get really tedious to have that many components. So we have some simple theorems and properties that we can use to simplify Boolean expressions. We call it Boolean algebra, right? It's algebra, but for ones and zeros. So you have some simple, stupid ones that are super obvious. Right? X or 0 only depends on x. X or 1 doesn't care what x is because or 1 is always 1. We call that properties of 0 and 1. No surprise. You have, so on page 37 apparently, because I don't have page numbers, which is awesome. You have a whole table of identities. I'm going to go through some of these, not all of these. But there are some interesting ones. If I have x or not x, what is that going to be? 1. It's always 1, right? Because one of those is always true. This one is always super helpful, which is the fact, well, first off, in case it's not obvious, x or y is the same as y or x. Just like normal addition, it doesn't matter the order. Same with multiplication. And just like with multiplication, if I have x and y or z, it is the same as x and y or x and z. Okay. Let's go find us a good example to go do some stuff. This one is an absolutely excellent rule. And you're going to learn to hate it. Not x or y is equal to not x and not y. Similarly, the reverse is true. not x and y is equal to not x or not y. Now, this is going to get really interesting for the homeworks because this property expands out to really complicated situations. And the general rule is you take each of the ands, and we'll go over this in more detail later, but I just want you to be aware. Each of the ands, which a lot of times is useful to note precisely, and flip them to ors. And if it's a x, it becomes not x. And with this overarching not, it's going away. So we'll walk through some examples shortly. We will do that today to show how interesting De Morgan's law is. Now what that does is De Morgan's helps you create the complement of something. So if you end up with logic that gives you an output of 1 when something is true, you can use De Morgan's law to end up with equivalent logic that outputs a 0 instead. So it creates the complement. This is useful when you have logic that is using a pull up instead of a pull down, right? So if you have an inverter in the output, and you go, oh, I designed all this logic and I didn't account for the inverter, you can just use De Morgan's law and flip it. So let's go through some pain of De Morgan's law. So if I have the expression that, how do we use this to simplify the expression? So, first thing that we do is we're going to write the and explicitly in there. That's because we don't want to forget that it exists. The next thing that we're going to do is we're going to go ahead and look at this, and we're going to exchange any ands for ors and any ors for ands. So what we end up with is A and B. This is an and, right? So we end up with or C or D. Right? Oh, they're doing this a weird way in the book. Anyways, we have a not A and a B. So we need A to be true, right? And we need not B. And then we have not C or D. So we're going to make that not C or D, which is just C or D, right? That and becomes an or. And this whole not, we invert, right? We not the invert. And then you end up with A and not B, or I screwed up somewhere. Because they're writing, sorry, I screwed up somewhere. Because they're saying it's C and D. And I've got to figure out why he did it that way. Oh, here's why. He's not simplifying that expression. So you can apply De Morgan's law to the whole thing or as parts. So he's just going to keep this part as whole rather than inverting it. So he's going to treat that as one chunk. So we're still going to have the not C or D, or sorry, C and D, but he's not going to worry about inverting that particular part. So he's going to selectively pull it out. If I give you a homework problem or an exam problem that has that, I'll say something like keep C or D as a single term. So then they're saying this equivalent, If you went back to the original and plugged in the ones and zeros, like did the truth table, you'd find them functionally equivalent. I'll give you some homework problems on De Morgan's and probably some other examples, in fact, in class, because De Morgan's is really interesting and kind of awful until you just do it a bunch. So they have an example 4.5, where they're going to walk through the simplification of this. For the sake of time, I'm going to let you guys do that because I like you guys going through and doing the step. If we end up with time at the end of class, I'll come back to this point and let you guys start doing it in class and walk through, because it's useful to step through the simplification where you have someone giving you the answers and taking the time to do it on your own. But moving on, there's this obnoxious idea that the book likes. You will find it as annoying as I do, but it's still useful, that sometimes in order to make things less complicated, you start by making them more complicated. Because sometimes you'll end up in a situation where something is simplified poorly. So if you have this expression, that looks reasonably simple, right? We can go back to our little table, and we can go use the logic adjacency theorem, and we can replace AB with this, AB, BC, and treat it as ABC or AB not C, right? Just logic adjacency, because if I have those, then we go back to another one, absorption. So I'll give you a secret. If I'm going to do this on a homework and exam, I'm probably going to give you a hint that you need to work backwards before going forwards. A lot of times these are going to be really tricky to see that you need to do until you're more experienced. So maybe I'll do something mean on the final or something just for fun. But in general, I'll give you a hint. And then you can go back to this little table. They don't even have it on there. They're calling it absorption, which if you have ABC or BC, right? You'll notice that you have B and C. This has to be true if this is true, right? Because in order for this to be true, I need 1, 1, 1, and then B and C is 1. So this term becomes completely redundant, right? Sorry, I'm trying to remember that you're there. You may have to want to move one seat back just to... So that quickly, obviously, becomes just BC, right? So that's what we're getting at. So similarly, if I have so now we're starting to see a similar pattern here, right? Where I have this AB, AB, ABC, AB not C. But we have this nice little rule about two terms, and also C or not C, right? What do we know about C or not C? It's always true. So end up, we can simplify this down to B, C, or B not C. And so the only thing that actually matters, because C is on both sides of that, is B, right? Because one of the, or the other of these is true, but B may or may not be true, right? So if C is 0, this C is 1, B is 1, that is true. B is 0, neither is true, no matter what happens. B. So suddenly we start cascading down to nothing but B. They use an example repeatedly through this book that I've skipped because, well, not entirely skipped, where they use a washing machine example because they think that using terms like hot and warm and blah, blah, blah is easier than ones and zeros. I disagree, so I've kind of stuck to logic. So if you want to go through the example 4.6, it uses a washing machine as an example. I think it's kind of boring. There's going to be lots of homework problems that are going to be using some of these simple Boolean, I say simple, they're kind of hard, especially to get used to when you haven't done them or if you haven't done them in a long time kind of thing. Where you're going to do these in the homeworks, they're going to pound into your head and you're going to kind of get used to them. If you get stuck or confused on these homeworks, use my office hours. Very few students are using them. So that means that there's time. And if you can't make it during the times, because I only have office hours on Tuesdays, Thursdays, and 1 hour Friday, you can try and set up another time with me. These homeworks, though, are going to be, I highly recommend doing them in advance of the deadline. Because you don't want to get up there and be like, I don't know what I'm doing, and I don't have time to go meet, right? And feel free to work together, talk together, and make sure that everything kind of makes sense to you guys.
I have a question about one of the laws, or one of the theorems or properties in the book.
Yeah.
There's this involution property, which is like not x is equal to x, but it's in not x is in parentheses.
Yes.
Can you explain that? Because that, in my mind, that doesn't really make sense.
So this is a really weird way of saying it, but it's just saying that not x
So in
is
the book,
x.
It just has.
It should have it on there.
It should have it on here
It's
in the
this
book.
print.
Oh.
Does it not
in the
have
book,
it?
It doesn't have the not x.
Oh,
It should.
it should. Mine has it. If
Wow,
yours
that's-
doesn't. Okay, so everybody look at your books if you've got it.
It's supposed to be that thing.
What page is that?
37.
So on page 37, you have an involution that should look like this, and apparently some of them are not.
Yeah.
Yeah, that about screwed me over.
Yeah, it doesn't make any sense that way.
And then also, maybe, okay, that one makes sense now since we figured that out. What about the complementary one?
Oh,
I guess I just need to talk it out in my mind, but you go over that one.
Absolutely. This one?
Yeah. And then the other one with the and.
Right. So, we can do this, we can prove this by exhaustion, right? That's one of those ways.
Put in 0 and 0.
Yeah, so if x is 1, this is an OR, right?
Yeah.
So then we have 1 or invert of x, 0. 1 or 0?
Which would be 1.
1. Similarly, if x is 0, 0 or 1 is
Okay.
1. So So there's nothing because of that inversion. Now, similarly, you're always going to end up with either one of those combinations on the ands.
Okay.
So it has to be 0. That AND gate can never be true.
So now I'm a little bit paranoid now that there was a misprint. Is there any other misprints? Because I don't want to like be doing this the wrong way.
Let me walk back, take a peek, and I will just link through to make sure.
Because this was like that. Yeah. I don't want to learn away and realize there was a misprint. Is this one? Yeah, this.
And all of those other ones look correct.
They're on lines here.
Okay.
There's a lot of it.
Yeah, there's these are.
I'm trying to find the games that they have with them.
Oh yeah.
They help a lot.
Okay.
Oh yeah.
Last year.
So let's do an example, right, where we're going to use the max terms of this. Okay. And we're going to start looking for some useful terms, right? And so we're going to start looking for things that we know exist in the theorems and trying to do our best to simplify them. So we can do things like, all right, well, I've got a term here and here that are the same. And more importantly, on that term, I've got a B naught or B, right? So the only thing that matters on those is the B2 or B1 term. Because one of those is going to be true. Similarly, can we do the same thing over here anywhere? Well, kind of, maybe. I've got two B2s that are the same, and my B naughts are the same, and I've got a B1 and B naught. Right? So that, same methodology, B2 has a bar, B naught doesn't. So therefore we can say That is equal to that. Oh, there we go. Sorry, guys. If there's ever something that looks a little shaky, like that, if you're suspect, go ahead and ask. I'm not going to be embarrassed. I'm not going to get this all perfect on the board. Yeah.
Shouldn't we be able then to put down more because the B2
Well, not quite, because the B1 and the B not don't simplify out. There's probably something you could do to rearrange that, but this is probably the simplest form as far as turning it into logic goes. So here we are moving into chapter 5. So chapter 5 is where we start getting into logic design, which I gave you that little sneak peek at the beginning of class where I showed you how to turn the sum of products into and an OR gate, right? Some of the things that we have to think about is that we have two terms. We have positive logic and negative logic. Positive logic is what we would normally think of as logic, where 1 is high, 1 is true. Negative logic happens when 0 is the truth. You will encounter both, and it has to do with the types of circuits that are actually being used. All of the rules hold true, whether it's positive or negative. You can invert them just fine, right? The algebra doesn't care what that representation is. A lot of times that you'll see, the reason that we use negative logic is really useful. One of the reasons, besides just the architecture of the circuit, is also that it's helpful to have a high signal to let the system know that it's active, and then it drops to 0 to signal begin. So one such example is in the 3610 lab that they're doing this week. They have a serial communication line where a PC is connected up to their FPGA. So in order for the PC to know that the FPGA is there, it puts out a high signal. But there's a machine on the other side that is waiting for that information. And when it wants to know the information is coming, it drops to a logic level low to say, get ready, there's data. So that would be low logic, where the dropping low, or negative logic, where dropping low says, I'm doing something. We do that same kind of thing with clears. So if you have memory and you want to reset it, we use active low clears. So that's another way of phrasing negative logic, is active low. So part of that is so that if the power drops, the natural thing that happens, because the power goes away, is it resets. So that means on power down, everything resets and goes back to begin, right? Very useful little system. They would like me to point out in this book that you can have mixed logic, right? You could have one block of logic that has a active low clear and an active high load. So it's like a block of memory. There's some data that wants to be stored in it. There'd be a clear and a load. And the clear, I would say, not clear. Active low. The other way of saying that is more type friendly is clear N, not clear. I'm going to get to erasing. So let me think. So our next class is Wednesday of next week, right? We have Monday off, so I'll see you in 1 week from today. If you guys, I'll post the homework that starts the digital logic, like the Boolean functions. And if you want to plan on coming to class on Wednesday, if you have any questions, we can actually spend a little bit of class time discussing that homework if you guys get some of it started. And I will make sure that it is due at least a day after that class period. So rather than just a week for the homework that'll pop out today, I'll give you like a week and a day or a week and 2 days or something, okay? Let me take note of that so that I don't forget. So, there's this idea of logic gates that we've mentioned, right? We've had the and, we've had the or, we've drawn the truth tables. Have we drawn the symbols for these yet in this class? Okay, so, and, A and B is as simple as A and B. Right, and we know the truth table for that. If both A is true and B is true, then C is true, and never else. And similarly, and I drew this up earlier, an OR gate. Also very important is not. The book will also define for you a buffer. And that's where this not gate originates from. So a buffer, all that's saying is that's the truth table for a buffer. Whatever is input is output. Now this is actually useful because, sorry, I don't want to go too far into the device physics of things because I know not everyone's had 1270 yet. But clocks can only drive so much, right? Like if you have a given circuit, it's really hard to have a small circuit powering your electric vehicle, right? But you might want a simple low-level voltage computer doing the thinking that's driving the wheels. So you might put in a buffer. So it does a little bit of thinking, low power, but the buffer can amplify that up to massive logic levels enough to drive your wheels. That's why you would have a buffer, is to drive a bigger load than the logic can think. Because you're right, your wheels are using 50 volts or something, electric vehicles about. You don't want to use 50 volts in a computer because that's just a waste of energy. So not, though, is used inside the computer all the time, and this truth table is just as simple. Just inverts. We also invert gate, right? A little bubble, you're gonna see that all the time. That's a not bubble, it's an inverting bubble. Very common symbol. You can actually add that bubble to an AND gate and make it a NAND gate. Same thing is true for the OR gate. And we now call that a NOR gate. And we went through these truth tables for these ones, did we? Just real quick, in case not. So normally in the AND, versus NAND, right? AND gate is really just take what the output should be and flip it. Because another way of writing this NAND gate would do that, would go and invert. Same thing. You wouldn't really do this because it's actually really easy to design NAND gates in logic using transistors, but it is functionally equivalent. But it gets more fun. This NOR, let's start with the NAND gate. Everybody likes NAND gates, right? So I'll start by redrawing the NAND gate. And its truth table over here, just to get it nice and clear, right, where we're going 0, 0, 0, 1, 1, 0, 1, 1, and we're at NAND, so we're going to go 1, 1, 1, 0, right? I would like you guys to take a moment to think about the logic, the truth table that is coming out of this. So this is an OR gate, poorly drawn, I apologize. And I'm just inverting the inputs of each of those. Go ahead and do the truth table. All right. I'm not going to rewrite these numbers, but what did we come up with for 0, 0? 0, 1? X?
1, 1.
Or 1, 1?
0.
These two are equivalent. Similarly, a NOR gate can also be implemented as that. Now, if you recall, thinking back, this operation is the same as what theorem?
Morgan's law.
Morgan's law, right? Flip the AND to an OR and invert your inputs. So now that we've done the gates, we can do a flashback to where I did that little example. And if I had something I have this expression. How do I want to go about turning this into logic? let's skip the simplification for the moment, right? Because this is what I would call fairly straightforward. There are some simple simplifications in here, but let's look at big picture, right? This is an and, this is an and. So we know we have three terms that are anded. We're going to start with the output gate, right? What is the output gate? This and this and this. And gate. And we know that and gate has three terms. And each of those inputs is OR. So let's just do one of these OR gates. We know it's A, B, and C. And we're pulling from here. So we can do not A, B, C. I'm going to be just going through 5.3 at this point, where they start introducing logic design, and they go through the steps for this for a little bit more complicated one. But they do point out, as I did, start with the output. Always work backwards from there, because your logic expressions are almost always going to have top-level ideas that are either tied with one gate. You're always going to have one gate for one output, right? And so the first step is start with the output. If you're designing active low, put a not, right? Nice and simple. If the logic expression is sum of n terms, so if it was, this is product of sums, or sorry, this is the sum, no, this is product of sums. Product of sums. If it is a product of sums, you start with the sums. If it's a sum of products, which is what we started with, you start with the OR gate, right? That's your output gates. Then they just say, start attaching the wires to the gates. Once you build this gate, build the next gates that are attached. You may cascade out a few times if you get complicated logic. Start attaching these wires, and you're just going to sit and repeat as you kind of cascade through your logic. You can be in a situation where you're going to have, and we will do some of these later, you're going to have only A, B, and C, and we know that A is knotted. In order to get that, we need to invert. Another way of writing that, remember, so I can put the inverter explicitly there, or I can just give it a little bubble. Okay, another nice simple example for this digital logic design. Let's start with a simplified equation. A little bit different form. Where do I start? What's the end gate? What's the last gate that I'm going to need? OR, exactly, OR. How many terms? Two terms. Then, all I need to do is, what is the first term? What is this gate going to be? And. What are my inputs?
Not A, B.
Not A, B. Similarly, this gate, I think, is pretty clear. Going to be an AND with A, B, not C. Exactly. Now, you can do, like, they go through this process of elaborating inverters, not inverters, but this is a great place to start. Now, there is a reason that you might want to start switching over to some other logic. Let me see if I'm skipping ahead of myself, actually, before I do this. Okay, I'm not really. It'll be fine. So, when you get to schematic design, simple vocabulary word, any of these that you see is a wire is what we call a net. So we use nets to connect to each other. Just to start ramping up some other terminology, because we are going to be working towards using VHDL, right? If you've looked at the class description. VHDL is what is called a hardware description language. It's a programming language that we will use to represent gates in the not too distant future, in fact. Now, VHDL has these two concepts where they don't just call these nets. They are, and these nets can reach all over a circuit. But if we consider this as a block of logic, right, that are going on, the inputs and outputs are called ports, right? Just like a computer port, your USB is the input and output port. And anything internal to the block is a signal. Now, because we are gearing towards, and the large part of this purpose of this class isn't just to understand digital circuits, it's built towards digital systems, which is the follow-on course for this. Now, for a digital system, we have to work with often the hardware we're given. The hardware in a FPGA, for example, is usually made up of strictly NANDs or strictly NORs. So you'll hear of things like memory that is NOR flash. That means the whole memory is made up with nothing but NORs. NOR gates and NAND gates are something called universal gates. Let me make sure I'm doing okay on time. All right, good. So these universal gates can be assembled in various ways in order to make any type of gate. Similarly, if I gave you just a little integrated circuit like we have in our labs that has, say it had NOR gates in it, you could use that little IC to wire it together to build any type of logic. So it is useful for us to be able to look at something like this, which is OR and turn it into either NOR or NAND. So the way we do that is we consider shouldn't have erased these in the beginning. We consider our NAND and NOR gates. Now what's kind of nice is that we can start identifying what this circuit roughly looks like. And so I already have an OR gate. Let's just doodle it in to a NOR gate. Oh, but I've changed the signal, right? But we know, thanks to a very useful question, that not X is equivalent, right, to X. So if we call these X, and we've done a not here, right? Now I've done not, so it's the same. This is a NAND gate. What are these?
And oh,
It's now a NAND gate, right? Because I have an AND with an inverted output, and I have an OR with an inverted input. NAND, NAND, NAND. I now have a NAND-only design in just one simple step. You can do the exact same thing if this is an AND gate as the output, and you'll end up with NOR gates. So now you can start to see if you're doing a design starting from a truth table, right? And you have the choice between min terms and max terms, and the min terms end up in product of sum, or sum of products, and the max terms end up in product of sums. You can now choose by design from a truth table what your output gate is, which in turn determines what your gate, your universal gate type is going to become most easily. Does that make sense? You go from truth table to sum of products or product of sums. The output gate of sum of products is what? That's where we have yeah, exactly. It's an OR gate as the output gate, which means this is AND. And when I have an OR gate to start with, I end up with NOR, right? And now as a designer, I can intelligently start with a truth table to get to the gates that I care about, or the gates that I have in my kit, whatever it happens to be. We'll call it 7 minutes early. I think that's a good place to stop.